Uh, you all have a glutton for punishment, apparently. So let's actually do it. Natalie, again, in a different location. Just at this point, she's
This is the
just
same as
messing with us.
last time. This is the same as last time. It is
Okay.
different, but like
You just changed the angle because you just still want to mess with us. Okay. All
yeah.
right. Let's jump into it. So yeah. Some general office hours. Okay, questions? Just go in.
I had a question regarding the what are they, improper integrals? How much work do we need to show for those to get credit? Like, do we need to do the breaking it up and replacing the bad points with limiters and approaches, whatever? Because you didn't do it in some of the trickier examples in the notes. So how much do we need to do to get credit?
Like what example were you thinking?
It's the one of it's the secant over square root xx, and I know you kind of just jumped in, or any of the ones basically where you went from I think negative infinity to infinity, you just kind of left it, which is fine, I get it. I just don't want to do that and then be counted off for not showing enough work.
Yeah, I mean, if in general, if you write something down the way I write it down, I'm fine with it. So you mean you don't want to, you want to know if you have to go through, I mean, the one with the secant, I think we did a comparison. You mean you want to know if you have to do something like this?
Yeah, but because you didn't do that on when you have to go into comparison, you can just jump in without replacing it with an arbitrary number, letter.
Oh yeah. So okay. I mean that's fine.
Okay, I just wanted to check how much we need to show for credit.
Yeah, I mean if you write things down the way I write them down, I'll be fine with it. So I do take the lead by example approach. So if you think I did it okay, if I get a little sloppy, you're allowed to get a little sloppy there. Yeah, I mean, and there comes a point in the future where it's like everyone knows they should do it, but they don't do it because they just kind of know, yeah, I know I'm going to take a limit to approach this, and they don't write it out. But yeah. Other questions?
Professor, is there a way that you could reopen the fake quiz? Because I didn't get a chance to complete it because I was doing test 1 prep on your website instead. Because I thought I was going to be due at midnight.
When did it close?
Like 5 minutes ago.
Okay. I will close it. Okay, it's reopened. I set it to close at 7 a.m. tomorrow morning.
Thank you so much.
Okay, other questions, issues, comments?
Can we go over a question on the the review sheet?
Sure.
I just was having trouble with 2C.
2C. How many? So 2C should be ignored. That's one of the ones you'd have to answer using the error formulas, and I'm not going to ask you about that.
Okay.
So that's why I had trouble, because I didn't actually do any of those examples. That's one of the things you skip.
Okay, sorry.
So for problem 2, make sure you know how to do parts A and B.
Yeah, A and B was good. Just C.
As well as just as a general rule, and you saw this in the fake quiz as well. I do want you to have some intuition for how the different approximation methods relate to each other. So for example, if I gave you an example, you should be able to tell me, okay, the right-hand rule would give me an overestimate while the left-hand rule would give me an underestimate, or the right-hand rule will actually give me a bigger answer than the trapezoid rule would give me, or something like that. You need to know how roughly, just as an idea, how the different methods actually, what kind of approximation they would give you, and be able to compare between the two. So for Simpson's rule, trapezoid rule, all of that, I would want you to first of all know how to apply them directly to an example. Like I give you an integral, I tell you the interval, I tell you the subintervals. give me a trapezoid approximation. You should be able to actually write it out and compute it. As well as I can say something like, okay, here's an integral. If I were to do the midpoint trapezoid and Simpsons, who would be bigger than who? Who would give me an overestimate? Who would give me an underestimate? Where you don't have to specifically write out the problem, but you do have to have some sort of justification for how they would behave. So in terms of the numerical integration, like those are the two main things I would say you need to know. Anything about errors or knowing how many terms you need to get this accurate, that has to do with the error formulas that I gave you. That's how you'd actually tackle those problems, but we're not really focused on that.
I have just a general question about the test. So do you know how many problems it'll be? And then like a second question. So like on the practice test, it was like 1 ABC, D, 2 ABC, stuff like that. So do those count as 2 questions, or does that count as like 7 questions?
Okay, so let me talk in terms of individual parts, like individual things you'd want to answer. So even if I have like Q1 and it has parts 1, 2, and 3, I would count that as 3 questions, right? So when it comes down to individual facts that you need, individual things that you need to do to calculate, whether it's parts of a question or otherwise, the test is going to be around 20 of those items. And a lot of them will be concept-based and some of them are calculations. So it's going to be a mixture of questions like this. Like I could ask you a question where, okay, numerical integration, don't do any computations, just tell me who would be the overestimate, right? And that would be, boom, 1 item, right? So you can expect around 20 such items. So for a quiz, on average, I give you guys 12 items to do in half an hour. So I figured 20 items to do in a full hour plus change is reasonable.
We have an hour and 15 though, right?
Yeah.
It's 8:15
So
to 9:30.
it will open at 8:15 and it will close at 9:30.
Are they
Thank you.
all gonna be like multiple choice selections, or the ones that you want us to show work, we just upload the work for?
Yeah, so it'll look just like the fake quiz. So there will be somewhere actually to show work, and those will be identified. It says, show your work for this problem. And there'll be a button that you can upload. So I do want you guys to actually test that out, make sure it worked. It is also worth mentioning that probably the quickest way to upload would be to upload a picture from your phone. You can actually log into Gradescope on your phone. So even if you have it up on your computer screen, you can actually log in a second time on your phone. And so the moment you do your work and you write something out, you can click the upload on your phone, take the picture, and you can upload directly from the picture on your phone. And so you can have that uploading while you're working on something else. So that'll to save the most time, that would probably be the strategy I would take.
I had a question about that. So I've been looking for like the Gradescope app and I can't find anything on the App Store, just the Apple App Store. Do you know?
Wait, I can
Gradescope
speak to
app.
this because I like did this last year for Calc 1. It's not an app. You just like log in
Yeah.
on Safari and it like
As far as I know, you just log in on
Okay.
your browser.
Oh, okay. Thank you.
Yeah, you just
That's
log in on
helpful.
your browser on your phone and just literally go to the same website, gradescope.com. You log in and go that. Yeah, I don't think they have an app. I always log in on my phone through the browser. That's probably a good idea though. We should suggest to them to make an app. They might be easier. But yeah, you actually log in on the browser on your phone.
Great. Thank you.
Are we joining the Zoom at 8:15 or at 8:30 like usual? You said you had clarified today.
8:30.
Okay.
This is like a question about the limit comparison theorem. So when you do the limit x approaches infinity of f of x over g of x, and L comes out to be like 0 over 0 or infinity over infinity, that's when you can use Hopital's rule.
L'Hopital's rule, yes, in those two specific situations. If you get a 0 over 0, infinity over infinity. And anything else you should know. I would also say in regards to that, So I would just put this as a note here. I expect you to know how to use L'Hopitals. Including situations where you have to rewrite, including rewriting indeterminate forms. So just to do a quick Calc 1 example of what I'm talking about, like I expect if you see something like this, I expect you to know how to deal with it, right? Like x to the x, right? X approaches 0 from the right. This approaches 0 to the 0, which is an indeterminate. I expect you to realize that when you hit such a situation, and all the indeterminates, these are like 0 to the 0, 1 to the infinity, infinity minus infinity, infinity to the 0, 0 over 0, infinity over infinity. So there are about 6 of them, and L'Hopital's rule helps you with these 2. Right? But if you have any of the others, you'd have to be able to rewrite it to be in a situation where you do L'Hopital's rule. So sometimes you can factor something off, sometimes you can just manipulate the powers. Now, when you have one of these guys where the power is the issue, like there's an infinity in the power, or it's a 0 to the 0, or it's an infinity to the 0. Like there's one of these guys where there's a power that's off. A very common trick that I would expect you guys to know is to rewrite using e's and ln's. So you can rewrite this as e to the ln of x to the x. And that would be e to the x ln x. So you'll notice 0 times infinity is another one. I always forget one of these indeterminate forms. So now you can also realize that limits pass through continuous functions. So when you write it like this, you only have to focus on what happens in the power. And now you realize that, okay, if I rewrite this, the power now behaves like 0 times infinity. In fact, negative infinity. So you can rewrite that as something like ln of x over 1 over x. And this, you'll notice, approaches infinity over infinity. In fact, negative infinity over infinity. And that means you can use L'Hopital's rule. So L'Hopital's rule says, if the limit exists, you'll get the same answer if you differentiate the top and divide by the derivative of the bottom. And so this just becomes e to the limit of minus x as x is approaching 0. And so that's just e to the 0, which is 1. Right? So this idea of like rewriting with e's and ln's to get a power to behave itself, you can do that. Or yeah, like and I just showed you an example. Like if you see 0 times x ln x, you should recognize that this would approach 0 from the right. You should recognize that this would approach 0 times infinity, which is an indeterminate form, but it's not a convenient one. So I should be able to like rewrite this like as 1 over x or something like that, and that gets it to be a nice form, and that's like L'Hopital's rule can work. So I can apply L'Hopital's rule at this point, differentiate the top, differentiate the bottom. And so that would give me 0. I also would expect you to remember how E is defined, limit as n approaches infinity of 1 plus 1 over n to the n. You should know that that should give you E. And in fact, E to the x is going to be the limit as n approaches infinity of 1 plus x over n to the n. Right, so things like that I would expect you to know. So yeah, L'Hopital's rule I expect you to know. I expect you to be able to rewrite indeterminate forms to apply L'Hopital's rule. And I expect you to know what E is as a limit. So just remember those. There are other ways. You can write it as reciprocals as well. So if you can do it as n goes to 0 of 1 plus n to the 1 over n, that's a similar thing. Yeah, probably the ones with infinity are most used. You can also notice that this is literally like limit as n approaches infinity of n plus 1 all over n to the n. That's the same idea. Right. So when you see things like that, you should realize that they're indeterminate, and you can either you can figure out that this is E because you can rewrite this guy in the same way that I rewrote this guy and actually come to the point where you realize the limit is E to the 1. But it's good to just know that guys that look like this actually approach E in the first place. So yeah, L'Hopital's rule, I'm assuming you have that. You can use that and you know how to use it.
Can we do 1C from the mock test on the website?
1C.
It's the one with the Weierstrass substitution.
Yeah. Let me copy and paste. Come on, stop misbehaving. Okay, so there we are, that guy. Okay, so tell me about the Weierstrass substitution. So what would your dx become under that substitution?
2 over 1 plus t squared dt.
What does your cosine of x become?
1 minus t squared over 1 plus t squared.
So like that you should know. You should also know how to find sine of x. And so what you would do is you would actually go through, and if this I call it I, you would actually go through and say, well, my I is the same as with this substitution, 1 over 4 plus 1 minus t squared over 1 plus t squared times 2 over 1 plus t squared dt. So that'll be 2 on top. You'd have the 1 plus t squared. You're going to take that and you're going to multiply the 4 and multiply that. So you get 4 plus 4t squared. And then you just get plus the 1 plus t squares would cancel, 1 minus t squared. So this leaves you with 3t squared, because the 4t squared minus the t squared, plus 5. dt. Which there are tons of ways to actually approach this one, but probably the easiest way is to think of this as radical 3t all squared plus 5 dt. And by thinking of it like that, one thing you can do is like a u equals radical 3t, your du equals radical 3 dt. So this integral becomes 1 over radical 3 times integral of 2 over u squared plus 5. And so now you just, you actually realize that this looks like root 5 squared. And then you would apply the rule. We know that 1 over u squared plus a squared du is equal to 1 over a tan inverse u over a plus c. So this is going to be 1 over radical 3 times 1 over a tan inverse of u over a plus c. And so now you plug in, so this is 1 over radical 15 tan inverse, your u was radical 3t. And your t was the,
Is it 2 over radical 15?
yes, there's a 2. I missed a 2 from, because there's a 2, so it's 2 to the left.
Do you also want to factor out the 2 when you factor out the 1 over square root of 3? Is that when you would factor that out to get the?
At any point, you could have done it here.
Okay.
It
doesn't affect the forming or the form of the, or I guess it doesn't really
no,
affect the
yeah,
form.
no. So we have the 2 here. Yeah.
Would it have also worked if when you had 2 over 3t squared plus 5, you factored out, what did I do? A 2/3, and you had like t squared plus 5/3, and then you took.
Yeah, you would end up
Okay.
with the same thing. So if you had like 2 over 3t squared plus 5, or you could factor out a 2/3. That would give you 1 over t squared plus 5 over 3 dt, which you can think of this as 1 over t squared plus radical 5 over 3 squared dt. And so this would give you 2/3 times 1 over a, so that's radical 3 over radical 5, tan inverse of t over a. And of course, the radical 3 would cancel into this, radical 3 times. You would end back up with the radical 15 in the denominator. And here you'd end up with radical 3t over radical 5 again. And then you can, that's tangent x over 2. Yeah, so like I said, there are actually tons of ways to approach this. The hardest way would be for someone to see this and try a trig sub. Like that would make it a lot longer. But this is something that, you know, I when I write tests, this guy shows up a lot. Because an integrals like that show up a lot in general. So I often put guys where you would need that formula. So that's actually one of the formulas that I do expect you guys to remember and be able to apply. It'll save you from doing trig sub in the middle of an already complicated problem.
I have a question from the homework. I think it was for 7.8. It's the from 1 to infinity.
Wait, so hold on. Homework 7.8.
It's one of the ones that's in like the back of the textbook. I think it's problem 51. It's the integral from 1 to infinity, x plus 1 over the square root of x to the 4th minus x.
Okay, and what were you supposed to do?
To tell if it diverges or converges.
Oh, so probably a comparison would work here. So I would compare to that. So this guy would look like, well, 1 over x plus 1 over x squared. And I know this diverges. It diverges because of this part, right? It's a 1 over x to the p where my p equals 1. And so now, do I know who is bigger?
Wouldn't the one on the right be bigger? Which means having the knowledge that it diverges doesn't help.
You tell me, is it?
I think it is. I'm
Because I mean, you had a
very likely
minus
wrong.
x originally. So to go from a denominator where there was a minus x and then I had to add x, right? So the denominator on the right is bigger, right?
Yeah, cool. That would be why I didn't understand how to do it.
Yeah, so the denominator on the right is actually bigger because it was the minus x. If it were a plus x, it would be how you said it. But to go from the original to the guy I'm comparing to, I had to increase the denominator. I had to add an x I had to add an x. To go from the x to the fourth minus x to an x to the fourth, I had to add x. My x is a positive number, so my denominator is larger because I'm adding a positive number to it, which means that that fraction is smaller. And so I actually know that this goes that way. And so the integral diverges by comparison.
Could you ignore
If I wanted to, if you didn't know this, if you didn't see this, you could do limit comparison. In which case you would take the original and you would divide it by the other one, which means like you're multiplying by the reciprocal. And then you find the limit as x approaches infinity of that. The x plus ones would have canceled. You would find the limit. And here you would end up with like the radical of x to the fourth over x to the fourth minus x. And that is 1, which is greater than 0. So both integrals do the same thing. Since the second integral diverges, then the first integral diverges by limit comparison. So you have a couple options. So limit comparison can come to your rescue if you mistakenly think that if you mess up on the inequalities. Here, direct comparison could work, but if you didn't notice that, you could do the limit comparison. And in the case where if this were a plus x, then direct comparison would not work, and I would be forced to use limit comparison, right? And because if this were a plus x, then this one would be larger, and so divergence means nothing. And so in order to conclude that this guy would also diverge, I would do the limit comparison. Once the limit of the ratio is a positive number, they behave the same.
Could we go over number 3 from the fake quiz?
From the fake quiz.
Yeah. Like
Okay, so this one.
yeah, like I knew the first one like was the direct comparison, but after that, like I just didn't know if it was would be like direct or limit comparison, like which would be better.
Yeah, so okay, so for the first one, you can compare this to if you remove the 1 and just compare it to x to the 3/2. So whose denominator is smaller? So who's bigger between these two?
The one on the left. Or no, sorry, the one on the right is bigger because its denominator is smaller.
So the one on the right is bigger. So it goes like that.
Yeah.
Right? And this we know converges. So this one converges. So this converges. This converges, so that converges by comparison.
Wait, really quickly, I understand this, but didn't we just say that if there had been a plus in the other one, in the x to the 4th minus x, if there had been a plus, that we wouldn't have been able to use?
Right, because in the previous
conversion?
example, the guy we compared it to actually diverged.
Oh, right. Okay. Thank you.
Right. So if this, in this case, if it diverged, we'd be in trouble. Like it wouldn't say anything. So in the previous example, we had a divergent guy that was on the right. So now we can look at the other one, radical x plus e to the 3x. E to the 3x. And again, for something like this, we kind of follow a similar concept. Remember when we had like polynomials, we knew that we just ignored the highest powers. You kind of want to generalize that concept. It's probably where you want to live most of the time. So here, if I have this integral where in the denominator I have a square root of x and I have an exponential, who's the dominating power? Who's the dominating function, right? The exponential,
Yeah.
right?
Yeah.
Okay, all right, take care. I know someone has to go, but I'll post a recording of this session. I don't know who's going to be able to watch it in time, but I will. So who's the dominating function here? Well, it's the exponential, right? So what I would do is I would ignore the radical and compare to just having the exponential in the bottom. Now, here, of course, because I took away a radical x, the denominator on the right is smaller, which means the fraction is bigger. So this is larger than that. And this one is actually something that I can integrate pretty easily. So I would actually do that. We can integrate that here. So be minus a third e to the minus 3x. And I think this is what Kendall was talking about earlier. Do we have to write the limits and blah, blah, blah? Like if you want to save time, you don't. Like you cannot now see if I plug in an infinity, it goes to 0. Plug in the 1, it goes to e to the -3 over 3. So this converges. So original converges.
Professor.
Yeah.
And then if the question was like, what does it converge to? Like we would have to.
You wouldn't be able to answer.
Oh, okay.
Yeah. So, like I said, there are a few series tests where it tells you what they converge to right away. The geometric series test is one of them. I know if it's geometric and it converges, it goes to a over 1 minus r. But in general, you won't know. So there'll be a few instances where we'll be able to figure out what some series converge to, but in general, it's not something you would know based on the series test. Same for this one, e to the minus x over x. So if I have like 1 to the infinity of e to the minus x over x dx, well, this is just but that guy, if I replace e to the x with an x, that's actually makes a larger denominator, and this one converges.
Can you just go over like how and why you did that?
Or, hold on, or you could follow the last procedure that I mentioned and just realize that getting rid of the x would also create a similar thing to happen. And this I can compute that this actually converges to e to the minus 1. Okay, so now going back, what I did here was I replaced the e to the x with x, right? And I just know that e to the x is bigger than x in general. One is exponential, one is not. So if I replace the e to the x with an x, I actually get something smaller in the denominator, which gives me a bigger fraction. And it actually gives me an integral that I know about already. Conversely, if you follow the strategy of just always focus on the bigger guy, I would ignore the x and then realize that, again, that's making it smaller because I'm now dividing by an x in the denominator, and then I can get to this. Either way, you want to get away from the x e to the x. Having the x e to the x makes it complicated. But the nice thing with the comparison theorems is that you're literally allowed to ignore certain parts of things.
So then why do you not just like ignore the e to the x? Why do you replace it? Because when you like just leave the e to the x, you completely get rid of the x. So like, why are you replacing it?
You could ignore the e to the x, but then if you here's why that wouldn't work. If I ignored the e to the x, what if we ignored the e to the x, right? Then I would have to compare this would be compared to this, right? And I would know that this is bigger. But what happens to the guy on the right?
Diverge, so that wouldn't help.
Right,
Gotcha.
this diverges, so doesn't help. Yeah, so I made the kind of changes that I made because they actually put me in a situation where I can actually make a conclusion. So either completely ignoring the x or replacing the e to the x with an x can work. And this is something that we do sometimes. So another thing, another similar example is sometimes you have like x ln x in the denominator, right? Whereas this one you could integrate with a substitution and know that it diverges. But what you could do is you can compare to replacing the ln of x with x. And that would give a bigger denominator, which makes a smaller fraction. And I would have to, yeah, that wouldn't work in this case. What example was I thinking of? There was an example where if you replace the ln, sometimes you might replace the ln with x. I don't know what example I was thinking of. Maybe it was in the numerator. I don't know, forget it. But that's something you can do. Sometimes if you can replace a function with a different class of function that you know is bigger or smaller. So for example, I can replace if I see a factorial, and it's in a denominator, for example, I can swap it out with an exponential if it happens to be convenient. And I would know how that would affect everything. Because the exponential will be smaller than the factorial. So by swapping out the factorial with the exponential, I'll end up with a denominator and a bigger fraction. So you can actually do things like that. You can ignore parts of it. You can swap out functions for other functions. As long as you know how the overall thing is going to be affected, and you can make conclusions on the new thing that you developed, you're fine. So you have a couple of approaches. You would have many approaches for any one problem. Different people see different things. Just make sure that when you do make a change, you can actually make a conclusion based on that change. But other than that, there are no real rules. As long as you can replace things, as long as you know who's bigger than who and what I'm allowed to do, it's going to be fine. Other questions?
This is just a little side note, but like for the homework questions, like for 7.7 with the approximate integration, those error with the formula questions, do you want us to, do we just like not answer them then?
You cannot answer them, yeah.
Okay, thank you.
So that's just for people who want to actually go a little bit above and beyond. But overall, it's not going to hurt you if you leave them blank. Remember, I am giving you guys like, I forgot if it was 10 or 15, like a 10 or 15% leeway on the homework. Like if you leave off that question, it's going to be less than a percentage impact. It's not going to matter. Like if you leave off those two parts. Did someone say something?
I think in the syllabus it says it was 15. I think if you get an 85 overall, it'll be a
Yeah, so if you get an 85 overall, which if you get everything right except you leave those off, you'll be fine.
Okay, thanks so much.
Other questions?
I have one more question. It's one you did in the notes, but looking back, I don't understand it.
Mm-hmm.
It's the integral from 0 to infinity of x over x cubed plus 1.
Oh, well, you're telling me, so let's just actually write that down and go over again.
Sorry.
Wait, did I actually finish did I finish this question?
There's one more part of 3.
There's one more part. So this one, did we conclude that it converges? Yes. This does converge. This one does converge. And for this one, that guy actually, you would know diverges. There's a couple ways that you can do that. And then I'll get back to your question. So this guy here, our x is between 0 and a half, which means when we raise it to a power, it actually gets, the higher the power we raise it to, it actually gets smaller, right? So this is a weird situation. In this situation, the x squared is actually going to give a larger magnitude than the x to the 8th. So if I like compare this to, do this. Let's do like an x compared to the x to the 8th, and do limit comparison. You'll notice that the limit is equal to 1, which is greater than 0. So both integrals do the same thing.
I have a question.
Yeah.
How can you do the limit comparison if it's not continuous, because it would include dividing by 0?
Oh, I can add something here then. Would be a good thing to add. Maybe like a half squared.
Don't both functions have to be
We
continuous
have,
though? And
yeah, both would have to be continuous. So this would be,
isn't it just a general rule that when you're between 0 and 1, if your power in the denominator is greater than 1, that it'll diverge, and if you're between 1 and infinity, that if your power in the denominator is greater than 1, that it'll converge? Isn't that just like part of the general rule?
I don't think I gave you, you mean like this, 1 over x to the p? Or 0 to 1,
Yeah,
1
but
over
like,
x to the p?
yeah, like that rule that I feel
I
like
mean,
when I was researching that, I know we didn't talk about it in this class, but I do think, is that an actual thing?
yes, that does work. That always diverges. That always diverges when you'd have to go through all the cases. So if your p is greater than, if your p is equal to 1, then that diverges when you plug in the 0 because you get the ln. If your p is greater than 1, like a 1 over x squared, then when you integrate it, you still have an x in the denominator, and that diverges. If your p is less than 1, say it's a minus, like it's a -1. Then that would actually converge. This converges if your p is less than 1. Less than 0 if it's negative. If your p is between 0 and 1. Yeah, so you'd have to derive a set of rules for this, and then you can use that, yeah. I don't think I did that in this class, though.
So in this case, if this were something that were on the test and I used that rule that I had known previously, would that be okay justification for reasons why this
Yeah.
diverged?
Yeah,
Okay.
as long as you wrote it down correctly, yeah.
Do you have like any tips
So
for like how we
here-
should know? Sorry, you can go.
Come again?
I was gonna say, do you have any tips for like how we should know whether to like use a comparison or the limit comparison, or we should just like try to start solving the integral? Because like sometimes I try to start solving and then I get like stuck. It's like, do you have any tips for that?
Yeah, so I mean, at this point, you should kind of know whether you can do the integral or not. That way, like if I look at this and I'm seeing like 1 over the square root of x cubed plus 1, like nothing we can do, we can't really do anything about that, right? Like, there's no rule that we would know of. One thing I would say is if it just says which thing converges, meaning I don't care about the actual answer, I would probably try comparisons.
Okay.
Just as a general rule. And I'd probably get a direct comparison to work first. And if it doesn't work, then I try a limit comparison. In terms of strategy, that's probably how I would go about it.
Okay. Thank you.
Yeah. For this one, yes, we are not allowed to use the limit comparison test because it starts at a 0. I wasn't paying attention.
So would a question like this, would that be considered theory or would that be considered like computation for something that we might see on the test?
For this one,
Yeah.
technically it's computation, I guess.
Okay, thanks.
Because you do have to do some sort of calculations. You have to compare who's bigger, who's smaller. But this one you'd probably approach in this sort of way. Factor out the x squared. And then basically how I would argue, and this is justification, you don't have to come up with any exact answers or anything. You would sort of argue that, well, to actually do this, I would split it into partial fractions. Cx to the 5th plus dx to the 4th plus da da da, all over x to the 6th plus 1. And then you'd realize that these guys would diverge, because those you can actually do directly. But you can just state that they would diverge. I would take your word for it. And yeah. And so remember, when you're doing improper integrals and you split things up, if any one of the parts mess up, then the whole thing messes up. So that one doesn't converge. And in terms of justification, you can write that down. So if I don't ask you for a specific answer, anything that just tells me you're thinking along the right lines, like you're comparing the right things, you're breaking things down the right way, that would be good enough. Now let's go back to the earlier, the question. It was x cubed plus x, was that it?
It was the integral from 0 to infinity of x over x cubed plus 1.
X over x cubed plus 1.
And you did it in the notes. I just don't understand it.
Okay, well let's do it again. What did we do? How would you do it? Just like just start from the beginning and just
I
tell me
went
what
and
you
I tried to do by comparison and compare it
what
to
would okay, let's start there. What would you compare it to?
1 over x squared, because I took the 1 out of the denominator, so I got like x over x cubed.
Right, and so you would compare it to 1 over x squared. Okay, now the issue is you would have a 0 in the denominator, right?
Yeah.
And that's the problem, right? So having the 0 in the denominator puts you in a very peculiar situation, because on one hand, it's not continuous, so you can't really make the comparison. You can't do the limit comparison test or anything like that. So what we did was, to avoid having to deal with this problem, this is a problem, because it breaks our continuity requirement, can't use the limit comparison test, can't even technically use the direct comparison test, because the inequality doesn't even make sense if I put in the 1 over x squared in there when it's dividing by 0. So to fix that, what we do is instead, this is I, we think of I in 2 parts. Just integrate from 0 to 1, and then integrate from 1 to infinity. And the argument is, this part is just a number, so this is just a constant. And then this integral I would compare to. So, and here is where I do the comparison to the 1 to infinity of 1 over x squared, because I have a theorem that tells me how that behaves.
Okay, so you wouldn't split up the 1 over x squared from 0 to infinity, and then, because I did that and it diverged and then I got lost.
Right, so yeah, the having the 0 in the bottom there, it just puts you in a very sticky situation. Yeah, and I think it's too many situations to worry about. So that's why I just gave you the theorem where it starts from 1 to infinity. And so I would just break it up so that you can use the 1 to the infinity theorem.
Professor?
Yeah.
If we were on the exam and like, let's say like we were like Kendall and we didn't really know what to do and like we couldn't use those theorems, do you think that it would be better if we actually tried to solve the integral and find the limits that way in case if like we didn't know how to use one of the theorems?
It's an option. However, chances are if I put down an integral with the intention that I want you guys to use a comparison theorem, it won't be something that you can integrate by hand.
Okay. Okay.
Chances are, like I would put one that would kind of force you to
Okay.
use comparison.
Thank
But
you.
like in general, no. I think in a previous question, like in question 2 on the fake quiz, like all of those integrals, you can actually just do them. So if you don't want to worry about the comparison, you could actually just do those integrals. So it depends on the situation. But if we're in a situation where it's like, just use comparison and tell me what's going on, then chances are you won't be able to integrate it. But if you catch me slipping and I gave you something that you could just calculate by hand, just do it. Just like,
When you're looking at the largest powers for the comparison, can you also ignore other like numbers or variables in the numerator, like how you can do it in the denominator too, or do you have to include them?
you can, just be careful.
Okay.
So you just need to remember that if you ignore any like positive additions in the numerator, that makes the numerator smaller, so the overall fraction gets smaller. There's an inverse relationship, right? So when the denominator gets smaller, the fraction gets bigger. The numerator gets smaller, the fraction gets smaller. So you just have to be aware of the changes you're making. So you could also ignore the lower powers in the numerator. Just make sure you realize how that affects the situation.
Okay, thank you.
The questions?
Just a few questions. Will you post the fake quiz answers so we can see that we did them right on Gradescope?
Yeah, after the time passes, you'll be able to see the answers. After the time passes, you'll be able to see the answers, but let's see, can I can probably, I can, yeah, so I will download the answers page and show you guys then. Because now that I reset the due date, it probably won't show you the answers until after the deadline, which is in the morning at 7. Probably doesn't help very much. So yeah, I can print out. Maybe I'll post it here.
While you're doing that, could you also post the review fake test answers that were from the one that was like on the website?
Oh, I don't have the answers to that. Like I didn't write them out.
Okay, it just said like if people wanted you to, you'd post them.
Yeah, so I'll also post the answers to the fake quiz. But as for the review, like I don't have those now. So, I mean, if there's anything you wanted to figure out with that, like now would be the time to ask me.
I mean, I don't think I was necessarily confused. I just wanted to like go double check, make sure I was right.
Yeah.
I actually had something I wanted to clarify with the fake or the review test.
Yeah.
For 1D, it's the 2 like polynomials for the fractions. So I started with the partial fraction, like the method of partial fractions. And
You can't.
I solved it one way, and then when
You can't start with the partial fractions. It's not in the right form.
Well, I did like the long division, and then
Right. Yeah, you have to do that first and then try to worry about that.
Yeah,
So
I got it into the form and I solved it, and then I looked it up to see if it was right. It like split the fraction before doing the decomposition. So I just was wondering like why it seemed to do that on.
I don't know, like if I were doing this one, I would do something like, so let's actually go over it. I would do something like, yeah, try to get the denominator in the top. So I have x squared plus x minus 2. And so here I have minus 2x minus 2. But then when I added my x plus 2, I have to subtract that x and add that 2 back. So that would just be the integral of 1. And then I would have plus, well, this would cancel that. I would have minus 3x. So I would have that. Then I would check if this factors. Hopefully it does. Otherwise, I'd like complete the square and do like a trig sub, or if it looks like the arctangent one, I would do that. But hopefully this factors. Looks like 2 and a 1. Plus 2 and minus 1 should work. So then I can split this even further into something over x plus 2, something over x minus 1. And yeah, I would like do the cover up method. So if I cover up the x plus 2 and plug in x equals minus 2, I would get minus 6 over minus 3. And if I covered up the x minus 1 and plugged in x equals 1, I would get 3 over 3. So this becomes 1 minus 2 over x plus 2 minus 1 over x minus 1. So that's x minus 2 ln of x plus 2 minus ln of x minus 1.
Professor,
Yeah.
when you do the long division, or when you just do like the algebraic manipulation, why do you
Mhm.
have a minus there? Like,
Minus where?
like, so if there's a negative 2x on the top, aren't you adding 3x to make it x? Like, to get the negative 2x to be x, you have to add 3x. So wouldn't it be positive?
Let me make sure. So I added an x. Right, I had to add a 3x to get the x, right? So then I have to subtract the 3x to bring it back to the original,
Okay, okay, yeah, you're right.
right? So yeah, to go from the minus 2x to the x, I had to add a 3x, yes. But now I don't want to change the value, so I have to subtract the 3x again. So that's why we ended up with the minus 3x. Yeah, but I didn't even take the risk of figuring that out, especially when I'm on a test. I don't want to like do that in my head and mess up. So I literally just, I write down what I want, and then I cancel the parts of that I added. And these guys were, and the minus 2x minus 2 was just me recopying what was there in the original. It's this minus 2x minus 2. So I left the x squared alone. I added the x and subtracted the 2 to make it look like the denominator. And then at the end, I subtracted the x and added the 2. It'll all work itself out at the end. At the end, I get 3x minus 3x, and that was the right thing.
I don't know if you can like tell us this, but at least on the fake test, all the like sequence and series ones, they were the bonuses. is that probably going to look like tomorrow's test, or should I like spend extra time going over those for the real problems?
Oh, I'm definitely
Since
going to
they're
ask you
very
about
new.
sequences and series tomorrow, for sure.
Great.
So sequences you should know about for sure. And just know what it means for a sequence to converge. If a sequence converges, what does it converge to? In terms of series, you should know the basic ideas about series. So what a series is. You should know that a series converging means the sum of the limit of the sequence of its partial sums converges. You should know how to use a divergence test for divergence. Yeah, you should know everything up to test for divergence. So everything I discussed up to test for divergence is there. And the other stuff about the series, like general series, like you see on the fake first test, on the review test, yeah, those would be in the bonus. So you can expect the bonus to look like that. I'd ask you some serious problems in the bonus.
Do you have recommended lectures for the rewriting indeterminate forms, or do you think like what we went over at the beginning of this meeting would be enough to get us through the test?
It should get you through a lot, but I already sent those lectures that I forwarded you about limits from my Calc 1 class, goes over those situations.
Okay, thank you. And these
Yeah.
notes, will you post them like underneath a YouTube video like you usually do?
Which notes?
The ones that we're looking at right now.
Yeah, I'll do that. So
Okay, thank you.
other questions? So I think we're fine. I mean, just go over your basics, look over these strategies for integrals. I mean, at this point, if you did all the homework and you've been practicing, you should be fine. Just make sure that you look over the mistakes that you're used to making and any misconceptions that you used to have, and you should be fine.
Sorry, I just
Thanks,
have one
Professor.
more
Have a good
general
night.
question.
Good night, Natalie. Yes, Caitlin?
Sorry, in general, do you curve, or like, will this test be curved, or just like is in general is stuff curved, or is that not how you prefer to do things?
There's a slight curve already built in. So yeah, like in general, I don't really do any curving beyond that. But as I mentioned, this is on like class number 0, so maybe you don't even remember, but I do think of improvement as being very important. So if I know you're improving over time, it's more important to me than you being good from day one. So for the most part, if you can show that over the course, over the trajectory of the course, you kind of, you might have started off not great, but if you slowly build yourself up and there's like this trajectory of you becoming an A student by the end of the semester, then in my mind, you're an A student. So while I wouldn't technically apply a curve, it's kind of like I value the bad grades you got less than the better grades, if that makes sense. So I do believe in rewarding improvement. I understand that not everyone comes in on top of their game on day one, but if you just show me that you're improving, you're getting better and better, then that shows something that should be rewarded.
Thank you so much. That makes sense.
Okay. All right, so I guess we'll stop there. We can go so that I can get this video processed and I can plug these guys in. For the most part, the computational ones, like the ones that you see online that you would have done in person because you wouldn't have had computers, those were a lot more computational than the multiple choice questions will be. So if you want to check them, you can actually check it on like Wolfram or something like that. So you would be able to check your answers. So let's say maybe I can do that here. That's going to be annoying. Okay. Maybe I'll. Yeah, so what was the last question we just did? The integral. It was x squared minus 2x minus 2 over x squared plus x minus 2. Was that it? Yeah, you can check. See, that's we should have gotten that. Now, Wolfram Alpha might actually turn things around inside the logarithm here because it's assuming it's a complex valued. But just remember, for us, we would put the absolute values around this. So the 1 minus x is equivalent to an x minus 1. So if you look at our answer, where we got x minus ln of absolute value x minus 1 minus 2 ln of absolute value x plus 2, that's going to be here. So you could actually check your work by just literally typing into Wolfram. Yeah, so you can always check that way. So the ones that I would have given in person, like, are on the math department website. These are ones where it's not, I'm not going to ask some ephemeral concept question on a test like that. I would just ask you to compute this. So you can check all of the computations on Wolfram. So I would just like do something like that. So you type int for integral, type out the function, and you can do it. As well as, let me just mention, another nice one is Symbolab. Loading slowly. So this one uses templates. So it's a little bit easier if you don't know how you can type math specifically, without this. So you'll see it, it'll put the little thing in the power. So it was this minus 2x minus 2, and the denominator was x squared. It was plus x minus 2. Hopefully I'm remembering that. And then you can click that. Did I type the question out correctly, or did I?
I think that's right.
X squared minus 2x minus 2 over x squared plus x minus 2?
Yeah, that's right.
So what is this guy doing? I don't know what method this guy is using, but oh, I see what it did. So the nice thing about this is that it can actually help you. It'll show the steps of its work. Sometimes, I mean, it's like a computer system doing it. So sometimes it'll do things in a weird way. This will actually be equivalent to our answer, believe it or not. because like, for example, here, the 2/3 x plus 4/3, if you factored off a 2/3, you'd have x plus 2 in here. And so here it would be able to combine with this x plus 2. This also, if you factor off the 2/3, you have an x minus 1 in here, which you'd be able to combine with that x minus 1. So you have minus a third ln of x minus 1 minus 2/3 of ln of x minus 1. That gives you the minus 1 of ln of x minus 1. And yeah, so this answer is actually equivalent. But it's just this guy was not in our class, so he went a very complicated route and just it found the answer in a much more complicated way than it should have. But for the computer, it doesn't actually matter. It's a computer. It loves adding a bunch of stuff anyway. Yeah. So sometimes this will follow the best route, but sometimes it doesn't. Like when you're someone doing integration by hand, I gave you the strategy that's easy, yes, for a human being to do. Your calculator or computer might do something else because it has, you know, it has a few gigahertz processor behind it to do the heavy lifting. So yeah, that's actually an equivalent answer, believe it or not. But yeah. It's unfortunate that it made things so complicated. So you might have to do some work with this one, or even with Wolfram. Sometimes it just does something in such a complicated way that you take some time. But I think like most of all the integrals that I had in the review test, like with Wolfram Alpha, if you just type them in, it should give you pretty much the typical answer that you would get. So I would check my work like that, but yeah. So with that,
Thank you
I
for
think,
having office hours.
okay, no problemo. Good luck tomorrow. Don't stay up all night. So just review some things and then have a good night's sleep. And yeah, I'll see you guys on the other side.
Thank you.
Thanks.
Thank you.
Take care.